Welcome to the CEAT Research Seminar Series, Virtual Edition.
Next speaker is He Bai. He received his Bachelor of Engineering degree from the University of Science and Technology of China in 2005, and the MS and PhD degrees in electrical engineering from RPI in 2007 and 2009, respectively. From 2009 to 2010, he was a postdoc researcher with Northwestern in Illinois, and from 2010 to 2015, he was a senior research and development special scientist with Utopia Compression Corp. He was the principal investigator for a number of research projects on detect and avoid, cooperative target tracking, and target handoff in GPS-denied environments. In 2015, he joined Oklahoma State University as an assistant professor in the School of Mechanical and Aerospace Engineering. His research interests include robotics and unmanned systems, multi-agent systems, Bayesian learning, nonlinear control, and sensor fusion. His talk today will be on safe wind-aware navigation for collaborative autonomous aircraft in low-altitude airspace. Dr. Bai, take it away.
Okay. Thank you, Dr. Bundy, for the introduction. Can you see my screen?
Yes, we're good.
Yes, we sure can. Thank you.
Okay. Yeah, I somehow cannot see what you guys see. So
it's just not maximized. So we just
Let me do that. Yeah. Okay. So now it's good. It's maximized.
No, it looks like you're in a regular view. If you go to presentation mode, it should fill up the whole screen.
Presentation mode.
Down at the bottom. Are you in PowerPoint, right? Yeah, you should be able to go down to the bottom of your screen and hit the little.
This one.
Yeah, you want to, if you maybe stop sharing. I think it may be if you've opened the presentation, it's not seeing the presentation.
Okay, so let me stop sharing.
If you start the presentation
and then
share, then you can select the presentation.
Okay. Go here. Share my screen. This one. What about now?
Yeah, it's maximized now.
We see your entire screen.
Oh, it's maximized. Yep. Does the slide move?
Yep.
Okay. All right. Sorry for that. Good afternoon, everyone. My name is He Bai. I'm from Mechanical Aerospace Engineering here at OSU. So today, it's an honor to be here to present our recent NSF National Robotics Initiative project on safe wind-aware navigation for autonomous aircraft. So this is a teamwork with a number of faculties in our department, Dr. Gay, Dr. Jacob, Dr. Kara, and also Dr. Vance from Aviation Education. So let's see if I can move my slides. All right, so is the slide moving on your end?
Yes, you may be able to use your arrow keys as well to navigate the slides. So.
Yes. Okay, so this talk will just have two parts. I'll give you a brief overview of the problem and our solution, and then I'll talk about specific tasks that supports the solution, as we just started this project early this year. So you'll probably see more on the overall big picture rather than the progress on the on individual tasks. So hopefully through the presentation, we can attract your interest, and certainly I look forward to any inputs, any suggestions you may have on this project. So the problem we're trying to address is about small US technologies. So they have found a lot of applications recently, or for the past decade. For example, drone delivery, air taxis, they're kind of booming now. To make them safe, safely operated in the airspace. Some kind of traffic management infrastructure is needed, and that is right now that is being developed at NASA and also supported by various industrial members. But really, for this small UAS to operate safely in low altitude airspace, the wind effect cannot be ignored. The wind effect can negatively impact pilots' operations and also could reduce flight time if you're flying against the wind. And also potentially, if the wind is too large, it could cause damage, as shown, on this picture. And also, the wind could make your airspace management problem more conservative, or solution more conservative, because if you don't know much about the wind, also you cannot predict the trajectories of the aircraft, the small UAS, then you have to allocate a very large, very conservative airspace for that aircraft to finish its mission before you can allocate that same space to other aircraft. So a lot of limitations now is due to a kind of lack of knowledge of wind and how to predict the trajectories of the UAS in the presence of wind. So our objective is to improve that through a synergistic collaborative research between different aspects of the problem. So we proposed a solution that involves the pilot in the loop, and also involves wind estimation and prediction. So in here we start with the UAS on the right-hand side, and then they will be used to measure wind data and collect wind data. That wind data is provided to the ground control station to do wind prediction. And by doing the wind prediction, the ground control station can suggest new paths for the pilot to take, whether the pilot can choose not to take it, but hopefully the path is good enough for the pilot to take and save energy and improve the safety. So eventually the pilot will take that path and command a new path for the aircraft to fly through. So the project will have two parts. One is to create such solutions and tools to enable the solutions, and also to evaluate them in relevant environments, in simulation and in experimental environments that I'm going to talk about later. So to support this solution, or to realize this solution, we kind of look at various tasks, research tasks that we need to complete in the next 4 years. So essentially, the bottom part is more on the physics side. So we need to understand how to, model the low altitude wind, and how to predict it using data from small UAS. And then this two part is focused on the small UAS navigation, control, estimation technologies. And then this two part is focused on the pilot operations. How do we model the pilot performance given the wind gust, and how do we leverage that information to provide recommendations for pilot to accommodate their needs in the windy conditions. So essentially, if you look at the tasks, there are 3 dynamical systems interacting with each other. They include human, right? So human as one dynamical system. They include small UAS navigation and estimation, and also include the actual physics of low altitude wind. So we are looking at an interacting system that consists of 3 dynamical elements. And to support all these tasks, we obviously need experimental testbed to validate any of the work, and also simulation testbed. So in terms of the tasks, I mean, all of these tasks are addressing different kind of challenges in the current research community in unmanned aircraft systems, and also in human-robot interactions. And if we're adding all the dynamical systems, I talked about 3 dynamical systems, if we kind of put them together one by one, they are addressing kind of challenges in increasingly complex scenarios. So if we just look at the UAS by itself and its control and navigation technology, what's missing out there is a tightly integrated and real-time wind estimation, control, and instrumentation. So right now, multi-rotor UAS, they have some capabilities of doing wind and control, but they are not tightly integrated. The path blending doesn't take into the wind information estimated, and they're kind of loosely decoupled. And we feel that by tightly integrate them, there will be more benefit to the UAS performance. And if we further add in the fluid dynamics, the wind part, then there's a big challenge of how do we use these mobile sensors, such as unmanned aircraft systems, to increase spatial temporal sampling of the low altitude wind field, and also how do we improve the prediction based on the data collected from the wind field. So that's another big challenge out there. And once we put in the human into the picture, like the pilot and the aircraft interaction, then what's missing, particularly nowadays for small unmanned aircraft system, is an integrated framework to support their decisions in a stochastic dynamic environment. So right now they don't have the tools, they don't have the theory and tools to support their decision when there's gust and when there's wind. So these are the gaps we will be addressing in the next 4 years throughout the entire project. So far the project has just progressed in the first year. This is kind of the progress. We're getting towards the end of the first year. The project, we're decomposing that into kind of 3 phases. The first one is focused on infrastructure development, basically simulation infrastructure, some testbed we need, so that we can kind of decompose the task to individual research teams so that they can focus on their research in the next couple of years to develop wind forecasting techniques, wind-aware path planning techniques, and also path recommendation techniques. And towards the end of the project, the last year, we'll be focusing on integration and demonstration to look at real flight test data, to conduct flight tests to demonstrate, for example, path planning and path recommendation. So that's kind of the overall review of the project and what we're trying to address. As you can see, it's kind of an integrated project with various disciplines. So now I'm going to talk about individual tasks. The first one is about pilot modeling. So in this task, we're really trying to understand the pilot performance and how do we model that and how do we leverage that. So if you look at this is fairly common scheme where you have a human in the loop or on the loop, and you have a machine or you have a robot you're trying to control. They're integrated together. The idea here is how do we better combine the skills of pilot and also the aircraft controls into a tightly integrated system. But if we kind of opened up the investigation, you can see there are a lot of components inside human. So there's biodynamics of the human, and there's also, vestibular. This is about the balance. A lot of this has been investigated for manned aircraft. When the pilot is actually situated in the aircraft, you can look at all of these dynamics. But little has been done actually in the small UAS pilot modeling, particularly the one we're going to look at in this task is the wind disturbance. How does that affect the pilot? His brain, his reactions to that, and how do we leverage pilot skill to learn better controls in the presence of wind and gust. So towards that end, we're developing, this is led by Dr. K, we're developing reinforcement learning techniques, trying to model a pilot's behavior while they are flying a quadcopter under a wind condition. So the IRL framework here is particularly useful because we can use input and output data, for example, the trajectories of the aircraft and also the controls the pilot provided. And also we know the dynamics of the quadcopter. We're going to use all that information to learn what the pilot is trying to do, right? What's the pilot preference given the wind, some specific wind condition. The preferences of the pilot could be whether he or she wants to go to the waypoint, the destination faster, or he wants to avoid the wind first, or he wants to save the energy. So all of those reward functions or objective functions can be coded in as a reward function, and their relative weights between them will be learned through the IRL techniques. And recently, we have developed some nonlinear filter-based approach to address that. This approach is an improvement over existing techniques because it handles measurement noise and disturbances kind of in a unified kind of filtering framework, and allows us to address output feedback system kind of very straightforward. So here are just 2 figures showing the kind of what we develop actually works in a simulation environment. What's plotting here are this Wi tilde is the weight we estimate minus the true weight in our simulation. So you can think of that as an error. And we kind of divide by the true value to give a percentage error. So you can see all of these errors are going to 0. And all of these curves, you don't have to understand what they mean, but these are all variations of the method we developed. And they have different convergence properties, but they all converge to 0 when there's no noise. When we add noise in with different standard deviations, the common filter approach we taken is part of one of the approach here, actually gives much better performance compared to other ILL techniques we've tested. As you can see, the errors are much lower compared to others. So that's basically the filtering mechanism is taking effect in the method we developed. So we have all the theoretical tools developed. Now we're going to move into the actual application of this ILL framework for quadcopter control. So inside this diagram, we can show the pilot will provide information to provide its controls, velocity controls or yaw rate controls to the quadcopter dynamics. And by observing the input and output measurement and also the controls, we want to see if we can use our ILL techniques to learn the pilot model, to learn what really the preference of the pilot is through the process. So that's one thing we're currently doing. So that involves collecting data and also kind of working out the solutions by leveraging the experimental data. Another thing that's also relevant for human-robot interaction is the interface part. How do we present the wind information to the pilot? And how do we present the suggested path to the pilot? So here just showing a mock-up of something we had in mind. Again, this is a current work. We're looking into how to add wind information. For example, we can add this kind of wind information, or maybe we can add an overlay of the wind onto the using interface that the pilot sees, and also the suggested paths may be plotted. So we're exploring different combinations of these features to be used in the user interface. Okay, so that's the first task. The second one is about using sUAS for wind estimation, right? So for them to navigate in the windy environment, they need to know the environment, they need to know how large the wind is. You can put expensive sensors on the sUAS, but usually the cost of the sensors is on the order of $1,000, whereas your sUAS is probably just a few $100s. So we're developing a machine learning approach. Here we use a recurrent neural network as the learning approach. We're giving trajectories of the US, and we use that to predict how much the wind the aircraft is experiencing. So here's a short video to show, so you can focus on this. This is the yaw and pitch angles of the aircraft as it flies. And here, this is the, you will see suddenly there's a deviation. That deviation is due to a wind. You're going to deviate from your desired trajectory. So by leveraging that deviation and also leveraging the yaw pitch angles here, we can estimate the wind. So here you can see the two curves tracking pretty close to each other. And one of them is a true wind. The other one is our estimate of the wind. And not only this works for constant wind, also it works to some extent stochastic wind, where we have generated using different kind of wind models. So you can see the blue curve is the actual wind, and the red one is our prediction. And it's also better than some existing technology, existing approaches to wind estimation. So this is, again, existing work. What we're currently working on is one step is can we take that one step further to say, can we develop a nonlinear filtering algorithm? The reason we need that is to do path blending, typically for robotic system that involves filtering or estimator that provides a full state of the robot. So what you're seeing here is only estimate of wind. There's no estimate of the robot position. By putting that into the nonlinear filtering framework, we're going to provide state information of the robot at the same time, and also test it with real data. Interesting, there's actually a new paper coming out from another university. They tested our approach with other approaches and showed that our approach is actually better. So that's really reassuring that we should be able to succeed on this on this real flight test data. The next, the big next step is the data assimilation. How do we include sUAS wind measurements so that we can better predict the wind? So there are a lot of existing approaches using dynamics such as POD, but also recently there are a lot of interest in machine learning approaches using Gaussian processes and convolutionary neural networks. This is actually one example. This is not from our research, but it's actually very interesting. Recently from ETH, they actually used the CNN to predict wind velocities given a lot of training data. So we would like to kind of build on this to say, now you have a prediction model of the wind. Can we assimilate the wind information collected by the US to better adjust the model or better identify which CNN model we should use when we do the wind prediction? So that's the wind estimation. Once you have the wind, of course, we need to do path planning to get a better path for the US. This is a work led by, again, by Dr. K. So we're looking at how to use that wind information and how to really do a real-time path planning. So for this small US, the computational resource is very limited. Optimal control, optimal path planning is not very feasible. So we look at sampling-based approach. And we're currently building on one of the paper from Stanford that basically decouples the cost generation and also the path planning. So the idea here is we can generate all kinds of costs offline when we fly from any point A to any point B. And once we have that cost map, in real time, what we need to do is basically just generate a tree that connects from the endpoint and the initial point and the endpoint. So they call it a fast matching tree. So you can see you can connect from endpoint to the endpoint with a lot of different choices. And what's left is really just compare which cost is optimal, and that can be done fairly quickly. So we're taking that approach when we're building on top of it, saying, how do we add the wind information into it? Because all of the existing approaches, they don't consider wind that much. They just assume they fly in a kind of wind-free environment. And how do we take that into account? Next, we're going to move into simulation infrastructure, the development of that, and also some experimental development. So this is a simulation environment we're developing. We're trying to incorporate low altitude turbulence information into the ROS, which is a robotic operating system. So Dr. Kara is leading the effort on simulating low altitude turbulence, which we call the turbulence in the atmospheric boundary layer, ABL. So you can see the turbulence effect actually. So this figure actually shows it. At the very bottom of your ground, you have a very low velocity. And as you go up, you have larger and larger turbulence velocity, and you can see its dynamic effect. But beyond some point, you have relatively constant wind velocity. But the aircraft actually moves, is mostly operating in the low altitude space, so it's gonna the turbulence effect gonna impact the aircraft through this wind velocity. So we have actually successfully integrated that the data generated from large area simulations into the ROS environment. So this, if you're familiar with ROS, this is very commonly used in robotics community. Right now, they actually don't have the capability to incorporate the dynamic wind into the simulation. So we kind of recently just made a breakthrough to incorporate that. So on the left, you'll see the aircraft that doesn't have any wind impact. You can see its movement is very stationary once it reaches the desired point. And on this one, you can see the dynamic wind perturbation, where you can see the aircraft is kind of perturbed around. That's essentially the effect of the turbulence. And we want to leverage that effect, try to first understand, can we estimate the turbulence better? And also, once we can estimate better, can we plan the path better to avoid or to safely navigate in the turbulent environment? And also, we're working on the indoor experimental testbed. This is necessary, or this is desired, because when we go out to do flight tests, there are a lot of there's limitations and restrictions. Sometimes we don't know the ground truth of the wind. We have to leverage a tower, and then the tower is not at the same location as the aircraft. So that creates some assumptions in our work. So we want to see if we can do something indoor to better test our algorithm before we go out. So this is kind of a snapshot of what we're trying to do. We have, fans located at different locations. We have the aircraft flying, and we have motion capture system provide, feedback as an indoor GPS system. And then also here we have a small ground robot, which is shown actually here. This robot is in charge of collecting ground truth data, right? So when we generate a wind field through this fence, we want to know what kind of wind field we're having. So we developed this robot to essentially, this robot is controlled in ROS and through the motion capture system. And then there's a linear actuator that goes up and down at the desired height you want. And on top of that, you can see there's a wind sensor that just collects wind measurement. So we're going to use that as the ground truth. And of course, we can switch that out with other wind sensors if they provide better accuracy or better measurement, so that we don't have to manually move it around and then get the truth. Also, we are doing some. We're doing some flight tests with Dr. Jacob, and also we're some broader impacts. We're really, the second bullet point is what the nice about is we started collaboration with electrical engineering on some wireless channel characterization. And also, I want to thank all the faculty members for supporting this, and also thank all the students, graduate student, undergraduate student, and thank the support from NSF and some support from NASA EPSCoR. So let me stop here. Sorry, I just realized I'm 1 minute delayed. Sorry about that.
Very good. Thank you very much for your talk. Very nicely done. The videos were pretty compelling. The floor is open for questions. Please, if you don't mind, go ahead and unmute your video and your audio, and I'm going to stop your sharing, and we'll be able to see each other's screens. And the floor is open for Q&A.
Very, very interesting project. I was trying to figure out: are you estimating a mean wind or local gusts and turbulence? And can you comment on the importance of the accuracy of a flight dynamics model of the vehicle to your wind estimation?
Sure. Yeah. So those are very good questions. So our objective is really try to estimate instantaneous wind. So which means that involves the mean wind and the gust. That's actually in the community. That's what they're trying to do. But how good we can do it, that we need to demonstrate through simulations. In simulation, we do it pretty well, but in reality, we know there's going to be a gap. And the dynamics is also important. That's why we need this learning model. We kind of use that to calibrate out any dynamic effect. For example, the drag effect. We don't know the drag coefficient. We can kind of use that learning model to calibrate that. So that's very important. And without a good calibration model, we'll be off. We'll have biases in our estimate. Hopefully, does that answer your question?
Yes. I'm familiar with some approaches that rely on a highly accurate, like a priori flight dynamics model. So that's a very interesting innovation in your approach.
Thank you.
Other questions? I have one. Can you comment on the robustness of your algorithm? I mean, could this fly down and be in a hurricane? I mean,
that's a very good question, and I don't know the answer, honestly. So we're taking it from low turbulence to medium turbulence to high turbulence. We're going to see, because of course at that point the estimation is probably less a concern than the control. Does the thrust provide enough control to counteract the very strong disturbance from tornadoes? And so that's a separate issue we're not addressing here. We're trying to address mainly on the estimation side. Suppose we're given enough control authority, can we use that, and can we use the dynamics to recover the encountered disturbance of the wind? But yeah, that I know there are a couple of probably a few universities are looking into flying UAVs into tornado. And I think Dr. Jacob probably had more to say that. I think he's probably one of the leaders in doing that. Yeah.
Other questions, comments?
Dr. Bunting, we've got some messages that I do not understand what they mean.
Yes, I am dealing with that. Thank you very much.
Yeah.
I'm gonna remove them if they can't use English and explain. I can't it's so. Other questions, comments?
I just have a maybe general question about where you mentioned reinforcement learning can be applied in with helping estimation of wind. So how much? So one of the things that I know from, let's say, deep learning is that even though deep learning has been very successful, but it can be very sensitive to the inputs of the algorithm. So how sensitive the algorithm or the algorithms in your research are with respect to tuning these parameters? How do they perform? As Dr. Bunting mentioned, this again goes back to the idea of how robust the schemes are. But I think that's always a challenge in learning and estimation.
Right. So yeah, I think so. So so one of the reasons we're kind of taking the recurrent neural network approach and kind of move it towards estimation, kind of traditional filtering estimation framework, is it allows better to incorporate uncertainties in the system, covariance and noise. But in the machine learning aspect, there's also Bayesian learning part, which allows you to put a prior on your parameters and also your input, and try to use the data to change that prior and eventually give you uncertainty estimate of your estimate. So essentially, we can use that to create kind of an ensemble of estimate and to say, all of these estimates are possible, and that's the uncertainty characterization we gave to the next stage, right? So if we're taking that for wind prediction, we're going to tell you, my estimate is 5 meters per second, but then there's an uncertainty about 0.5 meters per second in my estimate. And then the next stage, you need to take that into account to propagate the wind model. And I think there are standard tools like ensemble common filter, particle filters, to allow you to address those uncertainties.
We have time for a final question.
One quick comment I have. One question?
Sure.
Sorry, I couldn't join the whole talk, but at least I know what you guys are doing. I enjoyed the last year.
You're on the last page.
Yep. So the work we are doing with you is mostly for 5G millimeter wave communication. The Army and the NSF, even the NASA, are highly interested in these terahertz and optical communications, where the positioning is becoming more a problem. Actually, the pointing errors are really serious. So especially the question I have, how soon do you think your algorithm will be ready that we can implement, or at the simulation environment, actually, we can start working on it to use for terahertz communication or optical communication, that we see how it's impacting?
Well, the simulation environment is close to ready. So I don't know if you see the video, we already have it integrated into the ROS. The nice thing about ROS is there are a lot of packages available. You can try different drones. There are a number of, what we're showing is just a quad, but there's hectocopters and a lot of things. We can just simply replace it. So that can be ready very soon. The actual flight test, probably going to take, I would estimate a year to a year and a half to make it really mature. It also depends on what you want to do, right? So the robotic arm thing we did, I thought it was actually pretty interesting.
No, that's really interesting, and we're still waiting for the results. But I was thinking for the optical and terahertz communication, that like 6G and beyond, actually, there will be interesting topics to see how we can really overcome this the hovering issues with your algorithms.
Yeah, sure. Yeah, we can talk offline on that. I think there's a nice opportunity.
Definitely.
Well, everyone, let's thank Dr. Bai one last time. We can clap hands and give reactions. I know we've figured out all of these very interesting tools that we have. Dr. Bai, thank you for your talk this afternoon. Very interesting.
If I can just say one last thing, I really appreciate this platform for us to talk about research, and also I appreciate all the support from our team members to allow me to present on their behalf. Really, that's a big privilege for me.
Well, I'm really glad that you said that. We've got a team here at in the college that have helped sort of with some of the marketing material. I do want to do a good job for you all, and would appreciate any comments or suggestions you might have that we can use to enhance this experience. We are surprised to be at the lunch hour, but our participation has been pretty strong. We at the top we had like 25 or 26. And that all worked really well. So I'm really excited that we've been able to get this started. Our next talk is on the 23rd. We'll have Dr. Hamadi and Dr. Aiken actually will be presenting. So we look forward to those two talks. There will be talks in November and December as well. So
I did have a sort of a suggestion. If there is anything we can do to incentivize graduate student participation in these. That would be. I know once we get back to normal, we can have free food, but right now.
so I would hope, and I am there. One of the folks on my one of my advisory group folks mentioned actually having grad students do presentations in this format. And I'm a little mixed with that. I love the idea. I don't want to run over top of what our programs already have. So I'm really open to do what needs to be done. And like you say, incentivizing grad students, boy, that's right in the middle of what we care a lot about. I'd love to see 20 or 30 grad students at this thing. I'll buy whatever license I need to accommodate them. But part of it though, I can tell you the big struggle that I have is I love being able to do this. The whole Zoom environment has been fantastic. We've been able to connect with people, but the piece that doesn't happen is me peeling off with one or two others after it's over and kind of going, wait a second, I don't understand this bit here. And here's something I've done. And how do you create sort of that spontaneous sort of networking, right? I mean, I could just leave the room, I could just leave it open and we could just chat for a while, and I don't see a problem with that. But that's the piece that we really need to try to recapture. I'm interested in that piece too. How do we really connect with each other when this kind of format, basically one person talks, everybody politely listens, whereas if we were in a room, there might be 15 different conversations happening, or 5 different conversations that would happen.
Maybe we can have like happy hours, and then we create different rooms once there's a kind of a mutual interest.
And I think if we can also shift sort of the expectation of what the talk should be. I mean, the talks sort of summarizing research are great as well, but I think if we can also sprinkle in some talks that go as much depth as you can in half an hour, but like on a topic rather than talking about a big project, or if you have those kinds of talk, those could promote more discussion. I mean, we need both, but usually in a forum like this, the speakers gravitate towards, I'm going to tell everybody about everything I'm doing.
Right.
So yeah, that would help if there was some more focused talks interspersed with the more broad talks.
And we might have a little audience in that case.
Yeah. I'm happy to try and give one of those and see what happens.
Well, I'd be interested in different. I may approach you about some ideas that you might have. I'm certainly very flexible about what we do. I sort of modeled this on what was done before, where we had sort of a intentionally divergent group. I didn't want to hear 2 from MAE back to back. I wanted to have multiple folks talking, but just trying to engage a bit informally would be really useful.
Professor?
Yes.
I was just wondering if we could get the recording. I'm a graduate student working on the second project which was presented, so that I could share with my other graduate students.
Yes, it's actually, I meant to mention that we were recording, and I forgot to do that. So I'm going to actually have to re-record my intro that I gave to you, Dr. Yousefi, and I'll tag that at the beginning. You won't be able to tell, but I do plan to have these recordings out and available. I have no idea on the web where we're gonna put them, but I'll figure that out later. So absolutely, the answer is yes. I intend to create somewhat of a repository where we can have these out there that we can use them and have it ready for folks to be able to view. You know, I'm really anxious about sort of your question about grad student engagement and grad student involvement. When I was at Virginia Tech, we had within just the electromagnetics group, we had basically seminars once a month that would be that would have 50 or 60 folks that would attend, and I had to present twice. It was terrifying, but as a grad student, it was part of a requirement to present in that kind of thing. And you know, I know we have 3-minute thesis. That's really an important communication exercise. That's much different than what we're doing here. You know, the question is, how do we get support and how do we get engagement so that we don't want it to be burdensome, but we want it to be meaningful and effective for them, and as a communication tool and
I mean, graduate student participation for them as speakers is exactly why we started the MAE graduate symposium.
Yep.
So maybe just that, but I gave a talk last week at Syracuse and it had 80 graduate students in attendance. So I was like, how did you do that?
So, how did you ask the question?
All of their PhD students are required to take a seminar class. I think once a year.
Okay.
So once every 2 semesters. Yeah.
I know my daughter's at Texas Tech right now in atmospheric sciences. She actually worked with Jamie on some meteorological modeling, but they are required. They have required seminars they've got to go to there as well. And I mean, I hate to add a requirement, but I'd like to be as invitational as possible. But
yeah,
you need to figure that out. You really do. I think part of creating a community of grad students, I think, is key. They're connected to each other.
It's also a double-edged sword, though. If we make a requirement, then we have to make sure we have enough seminars.
Yeah. Well, this is true. This is true. I definitely think this is part of the quest that I'm on in sort of trying to step into this. And I'd rather, I mean, this isn't perfect. We'll do the best we can with it, and it'll be good. It'll be good regardless. I'd rather be good than perfect. So, and get it done. So, any other comments? Great. Thank you for taking the time to be with me this afternoon. Like I said, the next one will be in a couple weeks, and then look for some scheduling out in November as well. And if you have some suggestions for me, feel free to reach out to me via email or give me a call. I'd love to hear from you more. But
all right.
With that, you guys have a great rest of your afternoon.
Thank you.
Bye now.